Hello, in this video we're going to study isomorphic graphs. This notion of graph isomorphism allows us to distinguish the properties of two graphs, and you see this graph isomorphism in fields such as mathematical chemistry, electronic design automation, and so on. So two graphs may appear quite different in their visual representation, but still be the same graph according to our formal definition. The graphs in the figure here, this one, these three, are essentially the same, except for relabeling in the third graph. So here, instead of the nodes 1, 2, 3, 4, we call them A, B, C, D. They have the same nodes, the same arcs, and the same arcs to endpoint function. Structures that are the same except for relabeling are called isomorphic structures. Here is the formal definition. Two graphs, they have set of nodes, arcs, and functions, are isomorphic if they are bijections f1, n1 to n2, f2, a1 to a2, such that for each arc A that belongs to a1 and function g1 of A that takes x to y, if and only if g2 of f2a is f1x to f1y. Let me explain this. The bijection for the isomorphic graph are in parts. So let's look at this graph here. So you have 1, 2, 3, 4, 5 nodes. While this graph here you have A, B, C, D, E. The question is, are they the same? Are the same structure? Are they isomorphic? So based on the definition, if we have a function that maps every node in one graph to every other node in the second graph, and another function that maps every arc in one graph to the other arc in the other graph, then they are isomorphic. So bijection meaning there is one-to-one and onto correspondence. So as you see here, if I just relabel them, I'm relabeling them as 1, we say, let's call it C, 2 is E, 3 is D, and then 4 is B, and 5 is A. So looking at this second graph, the functions that takes one arc to the other arc. So for example, A1 in the graph 1, that takes, it should take C to E. Here is C, here is E, and we call it E1. So that's what we have. A2 again, it takes C to E. Well, here is C to E. So we call it E4, and that's what we have. A3, it goes from C to D, C to D, and so we call it E2. Here is what we have. And so on. A4, so A4, it should take E to D. Here is E, and here is D, and we call it E3. So if we continue like this, as you could see, every arc in the first graph, A1 to A8, there is a map that takes you to an arc in the second graph. So this is one of the mapping. I could switch the, for example, A7, I'll call it E5, because A7, it just connects A to B. So I have two ways of connecting A to B, either E6 or E5. So this can be switched. And similarly, A1 and A2, I could flip. This is E4 and this is E1. So there is more than one map. But as long as you map every node in one graph to the other and every arc in one graph to the other graph, we have isomorphic graphs. Isomorphism in a simple graph. So this previous example, this was not a simple graph because I have graph isomorphism is easier to establish if we restrict our attention to simple graphs. So as I mentioned earlier, there is more than one mapping because of the parallel arcs. But here, if we restrict ourselves to simple graph, then it will be a lot easier. If one can find an appropriate function f1 mapping nodes to nodes and f2 that maps arcs to arcs, is trivial because there is at most one arcs between any pair of endpoints, so there is no ambiguity there. Here is a theorem. Theorem of simple graph isomorphism. Two simple graphs, so you have a set of nodes and arcs and function, are isomorphic if there is a bijection f n1 to n2 such that for any node ni to nj that belong to the set n1, and I and aj are adjacent if and only if their image is also going to be adjacent. So if this 4 and 5 are adjacent, that means the next one will be adjacent as well. Proving that graphs are not isomorphic, we must prove that the necessary bijection does not exist. A certain condition under which it is clear that two graphs are not isomorphic are, so if you look at one graph has more nodes than the other, then right there you say these are not the same graph, it's not the same structure. One graph has more arcs than the other. Or when you see, for example, this B is not isomorphic with A. They are not the same because this one I have parallel, but this one doesn't, and so on. One graph has parallel arcs and the other does not. One graph has a loop and the other does not. One graph has nodes of degree K and the other does not. So for example here I have B has nodes here of degree 3, but A or C, they don't have any nodes of degree 3. So right there, B is not isomorphic to A or C. And so on. So one graph is connected and the other one is not. So this is connected, this one is not connected, and this one is not connected. One graph has a cycle and the other does not. So that's all. This is our all easy way to look at one graph and see if one of them fell, therefore they are not isomorphic. So which of the following graph is not isomorphic to the other and why not? So I would say B. B, it has the node with 3 arcs, so this one is not isomorphic to A and C. But A and C are isomorphic. So if I name them 1, 2, 3 and name this A, B, C. This is one arc, call it A1 and A2. So this is easy, you could find this E1 and E2 and write down the map as I did before, and you'll see these are isomorphic. So here I would say A and C are isomorphic while B is not. So the side of the two graphs are isomorphic. If so, give the function or functions that establish the isomorphism. If not, explain why. So take a minute and think about this graph here. So it looks like the two graphs are isomorphic. As you see here, I made the node from graph A 1, 2, 3, 4 corresponding to A, B, C, D. And similarly, I will find the second function that maps every arc from one graph to the other graph to the other arc on the second graph. Since this is not a simple graph, as we see here, we have a parallel arcs. We have more than function f2 and also f1. You could choose differently. But here is one way of finding the f2 function that maps every arc in one graph to the other arcs in the second graph. Let's see this example. You could stop the video and think about it. We have 1, 2, 3, 4, 5, and also 5 nodes here. So right away I can think of, maybe I'll call this one A, B, C, D, and E, because they are connected, A connected with B and so on. But to finish up with the second function that maps the arcs to the arcs, as this is E1, E2, E3, E4, and E5. And then similarly, I could call this one A1, A2, A3, A4, and A5. And this way we could easily write the two functions. So as we can see here, these two graphs are isomorphic, and here is the function that maps the arcs and the one that maps the nodes. Let's look at this example here. So take a moment and think about it. So as we see, these two graphs are not isomorphic, and we have to say why they are not isomorphic. Because the graph B, the node F, has 5 degrees, 1, 2, 3, 4, 5, while no node in the graph A has 5 degrees. So therefore they are not isomorphic. And this is how we know if the two graphs are isomorphic or not. I hope this is helpful.